Okay, let's start. Can we start?
Yes, please.
Okay. Now we will talk about measurement, measurement quality. First, I will introduce some terms, some basic ideas. Okay, and before lunch, I will talk about how we can measure the quality of your skills. Okay, I noticed that we have some marketing students here, so you will know the concepts that I mentioned more. The first concept I want to talk about is unidimensionality. There are two meanings of unidimensionality. One meaning is that your variable, your factor, has only one dimension. It is not a multi-dimensional construct. What is a multi-dimensional construct? It is basically referring to a second order factor. Let me find an example. See if I can find an example. For an example. Here, this is an example of a higher order construct called engagement. We know that engagement has three dimensions: rigor, dedication, and absorption. Okay? And each dimension is measured by three items. This is not unidimensional. This is called multidimensional. So this is one explanation of unidimensionality. That means we should not have a second order factor. It should not have dimensions. In this particular example, rigor, dedication, and absorptions are unidimensional because they do not have dimensions under them. However, engagement is a second order factor. That means it has dimensions, and each dimension measured with some items. Therefore, engagement is not unidimensional. A second explanation of unidimensionality, in particular, when we talk about confirmatory factor analysis, means that each item can be used to measure only one factor. That is what we call unidimensionality in SEM. A lot of cases in the past, when people do not get good fit of a measure, they include covariance among the error terms, or they add another factor loadings here. For example, they add this. Because the model cannot get good fit, they include they include another factor loading. Now, X4 is used. What that means is X4 is used to measure both F1 and F2. This has violated the unidimensionality assumption. Okay, we don't have unidimensionality here. The problem of this is not acceptable in all management studies and psychological studies, although marketing people like to do this. The problem of this is X4. When you use X4 to measure both F1 and F2, you will notice that their covariance or correlation is inflated because you're using the same item to measure the two factors. Therefore, they must be correlated based on this. So this correlation is inflated. And we say that F1 and F2 cannot have discriminant validity. They are not different factors because you use the same item to measure these two factors. Therefore, we cannot have one item measuring more than one factor. Unidimensionality in SEM means that each item is only used to measure one factor. Have I made myself clear? In management and
Yes.
psychological studies, you cannot have one item measuring more than one factor. In marketing, occasionally you will see that. But if you do that, you cannot say F1 and F2 are two different constructs because you have the same item measuring these two factors. Then the relationship is inflated. And we will say it is tautological. So you cannot test the relationship from F1 to F2 because you are using the same item to measure F1 and F2. So this is about unidimensionality. We assume all cost loadings to be zero, okay? All cost loadings to be zero. It is very important for discriminant validity. The next concept I want to introduce is about what we call identification. Okay, if you remember our 5 steps, in step 3, you need to make some decisions. One decision is identification. Okay, that relates to the scaling of your latent variable. And imagine your latent variable here, F1, for example, is our imagination, is a latent construct. That means you cannot measure it directly. We use the X. For example, it may be 5 items, 4 items, or 3 items. We have X1 to X3 or X1 to X5 to measure the same factor F1. In the reflective scale, we use the factor to predict the observed score. Do you still remember in classical chi-square model, X equals to T plus E? The E is here, delta. This is the error term. The T is the true score is this regression equation. The intercept, tau 1, plus the factor loading, which is the regression slope, lambda 1 times F1. Okay, here. Now, let's focus on the factor loadings first. We have, if we don't look at the tau 1 at the moment, okay? X1 is the known information. We have 2 unknown here. We need to estimate lambda 1 and delta 1. So it is unidentified. Okay, we cannot use one parameter to estimate 2 unknown parameters. Maybe another example. Okay, let me ask you a different example. Okay, how do you measure distance in Taiwan? I need some interactions here. I need some answers. How do you measure distance in Taiwan?
Kilometer.
Kilometers, right? Eddie, are there any other ways you can measure distance?
Meters.
Meters, kilometers, okay? Or miles, right?
Mm-hmm.
Okay, we don't use miles, we use kilometers.
We measure by driving time,
Good. So you can also measure it by driving time, right? Okay. Or if you take the subway, how many stops? Or if you take the bus, you can also talk about how many stops. Now there's another way, okay? When we take Uber, how much does it cost? Okay, $20 by, okay, sorry, I use New Zealand dollar, okay? So $200 by Uber. So you will get a rough idea how far it is, right? This are all known scales that we have. However, if it is an unknown scale, f1, a latent variable, f1, then we don't know what is the scale for you to measure your latent variable. Okay, so what we will usually do is we use the first item to fix the scale by fixing lambda 1 to 1. Okay, so what that means is 1 unit change in f1 equals to 1 unit change in x1. So we are equating the scales of f1 with the scale of x1. Okay, so all the latent variables have ambiguous scales. Unlike distance, we know how to measure distance, but we don't know how to measure job satisfaction. We don't have a scale. We don't know what a 3 means or a 5 means. Okay, so we need to provide a scale. A convenient way is to pick the first item, and then we fix lambda 1 equals to 1, such that your factor has the same scale as x1. The other possibility is if we standardize f1, then the unit will become standard deviation. One standard deviation change in f1 will result in lambda 1 standard deviation change in x1. So there are two different ways. To set the scale. This is an example. In model 1, we fix the variance of f1 to 1, okay, such that we can estimate the factor loadings for all the 4 items and the residuals or the measurement errors for all the 4 items. The other way is we can arbitrarily pick one item, the x1, and fix the factor loading to 1, such that we can estimate the 1 here is fixed. We can estimate the factor loading of the other 3 items, and then we also get their measurement errors, and then we get the variance of your factor f1. So these are the 2 different methods for you to provide the scale, or we call identification. And we repeat, one way is to standardize f1 such that the variance of f1 equals to 1. In that case, we can estimate the factor loading for all 4 items and the measurement error for all 4 items. Alternatively, we can fix the factor loading of the first item to 1. So we have 3 factor loadings to estimate, 4 measurement errors, and the variance of your latent variable. Which one is better, model 1 or model 2? Hello? Hinghua prefer model 2. Okay, others?
The same.
Maybe I should learn about the voting system and WebEx. Okay, now, in fact, they will give you the same answers. You will notice that, okay, when we say we fix the first item to 1, in fact, what we do is we divide all these factor loadings by the factor loadings of the first item. So if we divide 0.44 by 0.44, you get 1. If we divide 0.88 by 0.44, you get 2. Divide 0.66 by 0.44, you get 1.5. Divide 0.88 by 0.44, you get 2. And this variance is nothing more than the square of 0.44. So basically, you can easily transform from model 1 to model 2. Statistically, they are the same. However, practically, we would prefer model 2 because it will give you the variance of the factor. And it is particularly important when you have a multiple group analysis. We need to allow different variance of the factor across group. If you use model 1, you are assuming the variance of this factor is the same across group. So I published a paper in 1999 in Journal of Management about testing measurement invariance. I stated that we should use model 2. In fact, model 2 is the default in M+ and Laverne. In Laverne and M+, you do not need to specify this because it is by default. M+ and Laverne will pick the first item and fix the factor loading to 1 to set the scale for your factor. So Tsinghua is right. Okay, we prefer model 2, and this is also the default in M+ and Laverne. Then you will say that, hey, sometimes we may want to get the standardized coefficients. Even for this model, yesterday we did that already. You can ask for the output for standardized coefficients. If you look at the last two columns, standardized all and standardized LV, then you will get the standardized solution already. So I would prefer to use model 2. As for model 2, should we just pick any of the item to fix it to 1, or anyone really consider before choosing which item to fix to 1? Okay, I got a question. Which item should we use to fix the factor loading to 1? The answer is it is arbitrary. Any item. In fact, M+ and Laverne will just pick the first item, and we don't know what is the first item. You can rearrange your item such that the first item is X2 or the first item is X4. So sometimes people say that, hey, we should pick the one with the smallest factor loading or the largest factor loading as X1. No, you don't need to. Okay, so have I answered your question? Is any item? No. The issue of identification is whether you have enough information to solve your estimated parameters. For this model, okay, let's say model 2, we will estimate 4 variance, residual variance, 3 factor loadings, because this one is fixed, 3 factor loadings, 4 residual variance, and 1 variance of your factor. So we are estimating 8 parameters. There are 8 freely estimated parameters. In model 1, it is the same. The variance is fixed, but we estimate 4 residual variance and 4 factor loadings. So the number of estimated parameters here is 8. So we know the number of estimated parameters. What is the number of known parameters? It is the number of elements in the covariance matrix. If you have 3 items here, 3 items, we estimate the SEM from a variance covariance matrix. In a variance covariance matrix, you have 3 variants on the diagonal, and the off diagonal are covariance. These 3 are exactly the same as this 3 because it is a mirror image. Okay, this is exactly the same as covariance 2,1, covariance 3,1, and covariance 3,2. So in a covariance matrix with 3 items, we have 6 known parameters, P equals to 6. Here we have 6. Number of estimated parameters is Q. How many parameters you want to predict? Degrees of freedom, DF. Yesterday, when we talked about the chi-square, we have degrees of freedom. Degrees of freedom equals to P minus Q. Now, let me ask you a question. If K equals to 4, If k equals to 4, what is p? No. If k equals to 4, how many known parameters do we have here? Ten. Good. Okay, 10. You can either extend this, so we have 4 variants and 6 covariants, or you can plug it into this equation. So it is 10. We just mentioned that you have the p, no, the p equals to 10, q equals to 8, q equals to 8. So the degrees of freedom equals to 2. Do you get it? Do you know how to estimate it now? Now, for a factor with 3 items, we know p equals to 6. What's its q? If we have only 3 items, how many parameters, 3D estimated parameters are there? Now, this example is 4 items. If we only get 3 items, how many parameters are we estimating? 6. Very good. We will have 3 residual variance, 2 factor loadings, and 1 factor variance. So degrees of freedom equals to 0. Degrees of freedom equals to 0. Okay, now do you know how to calculate degrees of freedom? It is important because there is a concept called identification. If degrees of freedom equals to 0, it is a just identified model. Just identified model. If degrees of freedom equals to 0, I think I answered the question yesterday that when your degrees of freedom is 0, can you test the model fit? The answer is no. You cannot test model fit if degrees of freedom is 0. You cannot tell whether your model is a good measurement model or not if you get 0 degrees of freedom. The only way that you can get your chi-square and other fit indices is an over-identified model. That means degrees of freedom should be at least 1 or more. Then you can tell whether your model fits the data well. It must be over-identified model. If k equals to 2, if k equals to 2, what is p? If you only get 2 items, what is p? Hello? P equals to 3. Okay? What is q? If you only get 2 items, what is q? Right, q equals to 4. So what is the degrees of freedom?
-1.
It's -1. Very good. This is called an under-identified model. For an under-identified model, you will not get any solution. Okay? So let me recap. For under-identified model, that means degrees of freedom is negative, you will not get a solution. For just identified model, degrees of freedom equals to 0, then you will get one solution, but you cannot tell whether your model fits the data or not because it is just identified. For over-identified model, your degrees of freedom is 1 or more because there are more than one possible answers. Therefore, we can tell whether your model fits the data well or not. That is for over-identified model. If I make myself clear, so you should have at least 1 degree of freedom to test the model fit. Now, the fourth bullet point asks about the number of items per construct. A lot of times people ask me, how many items do we need to measure a construct? My answer is 4, because for 4 items, only with 4 items, you can have an over-identified model. But you will see that a lot of studies in management, they use 3 items. And sometimes in marketing, they use a lot of 2-item scales. Okay? Then why can they estimate the factor loadings? It is because they do not estimate the factor loadings based on this factor. They estimate the factor loadings based on this covariance. They need to make use of the covariance of the 2 factors to estimate the factor loadings. So it is not a good practice. Let's assume, okay, it is a very, very complicated exercise, okay, what we are going to do. Now, let me first ask you, if k equals to 5, what is p? If k equals to 5, what is p? 15, very good. Okay, now assuming we have 5 items, the first factor measures by 2 items. I don't know if I can modify this. Okay, let me modify my model. Modify my model. So we have 5 items. First 2 items measure the first construct. And then we have 3 items measure the second construct. G equals to 15. What is Q? How many parameters we are estimating here? Oh, that's good. Xinhua, we have 11 estimated parameters. Let's assume that we fix the 511 and 52221. So we have 2 factor loadings here, 3 factor loadings here. We're estimating 5 factor loadings, 5 error terms, and 1 correlation. So Q equals to 11. Degrees of freedom equals to 4. So what I've just mentioned to you is, if this factor by itself is under-identified, you cannot test. This factor by itself is just identified, you cannot test the model fit. But if we put the 2 together, then we get degrees of freedom equals to 4. It is because we make use of the correlation or the covariance between the factors. That is not a very good practice. So I would suggest people, if you want to measure a variable, make sure that you have at least 4 items, such that each factor by itself will be an over-identified model. you can test the quality of your measurement.
Excuse me, I have a
Yes.
question. So earlier example, we have 2 items for factor 1 and 4 items for factor 2, right? And then,
3 items.
yeah, okay. And then it's over identified. And then, so why you don't recommend it?
The reason why I don't recommend it is because we can only examine the quality of this because of the covariance of the 2 factors. If you use this measurement model in another study, okay, then you will not talk about F2 with 3 items. You may be talking about another factor. Then all this will become different because the covariance will be different. Do you get my point?
I know.
Okay, so it is because this is over-identified only because you put the factors together, but the results will very much depend on what factors you put together.
Okay, got it.
Okay.
And I have a subsequent question. So, Professor Gordon, you mentioned in today's example, and for what's that? It's I think earlier you gave us an example about like a secondary construct, right?
Yeah.
Suppose in my model I have 2 separate secondary constructs, and then so together I have 6 unidimensional construct. In the measurement model, how would I instruct Levin or M plus to do that? Do I do that
I'll show
separately?
you later how to define second order construct.
Yes,
Okay.
but when I have 2 separate secondary construct, that's my question. So maybe
Yeah,
later.
yeah.
Thank you.
Today we are going to touch on examples with 2 second order constructs.
Wonderful. Thank you.
Okay. Even as smaller or local parts, we still need to ensure this local part can fulfill. So Tsinghua asked a question, okay? It's a very good question. Although the overall model is over-identified, but for this local model, part of the model, it is under-identified, and this part of the model is just identified. It is not a very good model. Some scholars say that we should not look at the model fit because this part is under-identified, this part is just identified, although the whole model is identified. Okay, so we cannot just estimate whether this part is good or this part is good. Because the overall model fit can only gives you the whole model. It cannot tell you part of the model. So the answer is yes, we should ensure that the local part, at least it is just identified, but better to be over-identified. Then there are some cases we talk about single items. Okay, sometimes we will not use multiple items to measure a construct. Example, if you ask your respondents about their age or tenure, you will not ask multiple items. Those are items we call single item constructs. Okay. We can include those in an SDM model, but we cannot estimate the measurement error. We cannot estimate the measurement errors. In a single item construct, you need to fix the factor loading equals to 1 and the residual variance to 0. That means you need to assume about the measurement errors. You cannot estimate the measurement errors if you have a single item. We will come across different scenarios of single items today. Okay. One example is that your measurement by itself is single item. For example, age, tenure, gender, education. These items, you will not ask multiple items. There's another possibility that we purposefully create using the submitted scale instead of the items to measure a construct. That is what we will cover tomorrow. We label those as reliability corrected single indicator. That is what we are going to do tomorrow. Now, Ming-Jie yesterday asked about refractive constructs and formative constructs. And I emphasize again that in structural equations modeling, we are based on the classical two-score model, such that we are dealing with reflective constructs. What we mean by reflective constructs is that the latent constructs cause the measurement variables. You still remember yesterday we have x equals to t plus e. Here we are using the t to predict x, and therefore we have an error. So this is the reflective measures, and in this way we can identify the measurement error for each item. The error results in an ability to fully explain these measurement variables. This is an e. Okay, we cannot use t to fully estimate tx. Oops. This is an earlier equation that we use on slide 92. We have the latent variable f here. We use this to predict x, so we have an intercept and a slope, but we cannot fully predict it, therefore we have an error term. This is a reflective measure. We use the factor to predict the observed variable. For formative measures, formative constructs, okay, they are different. Formative constructs use their items to predict the variable. For example, y equals to x1 plus x2 plus x3. Here, we are using 3 items to predict the score of y. This is called a formative constructs. For reflective constructs, we use your latent variable y to predict the item score. Formative constructs, we use the item scores to create your latent construct. Okay, you will notice that in this particular case, we cannot estimate an error term here. So you cannot estimate the measurement errors when you have a formative constructs. You can only tell there's also an error term here, but this error term only reflects how good these items can be used to predict y. It is not the measurement error of the items. One example is socioeconomic status. Sociology people like to measure socioeconomic status. Socioeconomic status, how do people measure socioeconomic status? They use their occupation, their education, their income, combined together, these are the x1, x2, x3, to represent socioeconomic status. There are different properties of reflective constructs and formative constructs. In reflective constructs, because we use the latent variable to predict different items. So different items this is x1. For x2, for example, it goes to x times y plus a. Similarly, we can have x3 equals to lx times y plus e. So here, in this example, we have 3 items to measure the same construct y. You will notice that because we use the same construct y to predict x1, x2, and x3, therefore, x1, x2, and x3 should be highly correlated. The items should be highly correlated in a reflective construct. Have I made myself clear?
Yes.
Because we are using those to measure the same construct. We are using the items to measure the same construct. Because they are highly correlated, that's why we can calculate convex alpha. Convex alpha are only for reflective constructs. The items are highly correlated. And we use the true score to predict the observed score. For formative constructs, x1, x2, and x3 are not necessarily to be highly correlated. For example, in socioeconomic status, education and income and occupation are not necessarily to be highly correlated. We just create the score y. Therefore, we do not have convex alpha for formative constructs. We do not have convex alpha for formative constructs. In SEM, how we can do this instead of estimating the vector model, we simply take the average of x1, x2, and x3 to represent y. This is how we can create a formative construct in SEM. Okay, in that case, they are not latent variables, but we call this indices or index. So these are the major difference between formative constructs and reflective constructs. There are 2 simple ways that you can determine whether you have a reflective construct or a formative construct. First, whether the items are correlated or not. For reflective constructs, the items should be highly correlated. In a formative construct, you will notice that the items are not highly correlated. So you can calculate a convex alpha for reflective constructs, but you cannot calculate a convex alpha for formative construct. Usually, a formative construct is defined as an equation here. Okay. Now, do you know how to distinguish the 2? The first way is whether the items are correlated or not. Now, the second way to distinguish is what happened first. In a reflective construct, I told you because we are using the latent variable to predict the observed score, that means the latent variable happens first before you can have all your observed variables. One example is you measure attitude. We cannot directly observe the attitudes. Therefore, we use your behaviors out from those attitudes to measure the attitude. So the indicators are the behaviors that are resulted from your attitudes. So you will notice that the factor, the latent variable should happen affecting your indicators. But in a formative constructs, typically we will have the indicators defining the factor, or the indicators happen before the factor. So 2 criteria. One is whether the items are correlated or not. Second is which happened first. In SEM, we typically deal with reflective constructs. Yesterday, I think Maxwell also asked about PLS. PLS is typically dealing with formative constructs. Really ask the question whether it is possible to have both reflective and formative constructs in the same SEM model. The answer is yes. It happens a lot of times, in particular in HR studies. As I mentioned to you yesterday, some measures of HR systems, they use 10 items and ask people to say yes or no for each item, and then they add up the scores. Those items are not necessary to be highly correlated. So you form an index. So if you want to include both reflective and formative constructs, you have a factor model for your reflective constructs, but for the formative constructs, you take average of the items, and that becomes a single factor, single item factor, because that is an index. That is how we include both reflective and formative constructs in the same SEM model. Okay? Now we'll have an exercise. Example A2 is about CFA. This is simulated data set from an article in Industrial Marketing Management. Okay, we have 8 latent variables. When there's brand equity, merchandising support, margin maintenance, special treatment, customer advocacy, relationship value, business growth intention, relationship maintenance intention. This article is about the relationship between the buyer and the vendor, whether they want to build stronger relationship. This is a marketing study, so they use 3 items to measure each construct. As we did yesterday, first we need to load the data file into R, and then we specify the model. Now you can see that for a measurement model, yesterday when we deal with regression, the symbol, the operator that we use is a slick. Today, when we deal with measurement model, we use equal SNCC. That means here we use X1, X2, and X3 to measure brand equity, BE. We use X4, X5, and X6 to measure merchandising support. A lot of times for these labels for your latent variable, we use the short form. Very soon you will forget what that BE represents. Therefore, I always add a pound sign and put down brand equity here. Further asked the question yesterday in the path analysis. We have all those square boxes, whether those are formative constructs. Okay, well, yes and no. You can say we treat it as a formative construct. Okay, but in fact, we just take the submitted score. We take the submitted score and consider those as if observed score without measurement errors. So we actually have to ignore the issue, whether it is formative or reflective. We just take the simple average score, the submitted score, to represent those constructs and treat those as observed variables. That is how we did our analysis in t-test and ANOVA and regression. We ignore the issue. If you have to classify those, you can say that we treat them as formative or index. Okay, so we defined our measurement model like this, and then we estimate a model. Yesterday, we put SEM here. The function is SEM. Today, we put CFA. But It doesn't matter whether you put CFA or SEM, you will get the same result. Here, I also add mean structure equals to true. That means we also want to estimate the intercepts when you put mean structure equals to true. And the summary, here we ask for the standardized equals to true and R square equals to true. Okay, so now can I ask you to run model 2? Okay, in fact, you have the code. Oh, okay, wait. You have the file, example A2. I'll code example A2. Okay. You have the file already. Okay, I'll code example A2. You can copy and paste the slide number 98, or you can open this file and run model A2. I'll copy this to my R here. In console, want to paste it here. So I've just run my model, measurement model. Have you run your measurement model? You can either copy and paste it from our code example A2 or from slide 98. You got your results? Hello?
Yes, I got the result.
You got the results, right? Okay. I copy and paste the results on the slides. Like first, we will look at whether first you will check at the bottom whether you get any error message or warning messages. If there are negative variance or correlation greater than 1, then you will get a warning message. You don't see any warning message, so that is good. The second thing that we will do is to read the fit indices. Here, you can see that we have 224 degrees of freedom, and the chi-square is 342. If you look at the p-value, you will reject your model. If you look at your p-value, you will reject your model because the sample size is pretty large and empirical studies. This is 527. But if you look at CFI, you will notice that it's 0.98, 0.98. Okay, it is very good. TLI is also over 0.95. RMSEA is 0.032 and SRMR is 0.038. So we will report chi-square with 224 degrees of freedom equals to 342. CFI equals to 0.98. RMSEA equals to 0.032 and SRMR equals to 0.038. The fit indices indicates our model fits the data well. Do you get it? because our MSEA is lower than 0.08, SRMR is lower than 0.08, and CFI higher than 0.95. Our model fits the data well. Here, do you notice that the factor loading for the first item are all 1? Because it is by default. It is by default. The factor loading of the first item equals to 1. But if you look at the last column, the standardized all, you get back the factor loading for the first item. Okay, you get the factor loading of the first item back here. In this particular case, for the standardized all, that means we set the variance of BE equals to 1. That is the standardized all. So you get the factor loadings, you get the covariance among the 8 factors. The last column, the standardized all, becomes the correlation among the 8 factors. You got the intercept. You got the variance for the items. These are residual variance, and we got the variance for the 8 latent variables. We also get R squared. We'll talk about this later. So we have the fit indices. We have the estimated parameters. Again, by default, it sets the factor loading of the first item to 1. But you can also look at the last column, which is a different identification method, which fix the variance of the factor to 1, and therefore we can estimate factor loadings for all items.
So Golden, is that the 2 steps conducted by R? Because the first step is actually set to the factor loading for the first item to be 1. And then the second step is actually have the variance of the factor being 1. So we can estimate the estimated standardized factor loading for all items.
In fact, they only estimate it once with this part, the unstandardized. These are the unstandardized factor loadings. But just like what I showed you in this diagram, you can easily convert from an unstandardized to standardized.
Oh.
So what Vern has done is estimate unstandardized and convert all those to standardized. Okay, so it doesn't need to estimate the model again.
Okay.
Always estimate the unstandardized. And also, whenever you test whether these are significant, you need to use the unstandardized to test. Because if you estimate a model with the standardized coefficient, the standard errors can be incorrect. You get that?
No.
The standardized coefficients, the standard errors for the standardized coefficients can be incorrect. Therefore, we always estimate to test our parameters. We seldom test factor loadings, but we will test regression coefficients. Then we use the unstandardized to test. We don't test with the standardized. But in factor loadings, although we estimate the unstandardized factor loadings, later on I will show you that the standardized is more important. Standardized factor loadings are very important, where we estimate the reliability and test for convergence validity. Now, yesterday to today, we use the estimator maximum likelihood. Yesterday, I also mentioned that maximum likelihood has an assumption that your raw data are normally distributed. What if the data are slightly deviate? It cannot be too much, okay, but they are different from normal distribution. They are not multivariate normality. then we should use the estimator MLR, maximum likelihood with robust standard errors. It will adjust the fit indices and standard errors with a scaling factor to account for non-normality. In fact, it is my practice now, all the estimates, except for bootstrapping, all the estimates that I make are using MLR. So I don't need to worry about the normality assumption. Okay, so we can run your model again by running a different model and adding estimator equals to MLR to see what are the differences. Copy and paste these two lines into my R. So I got a new set of results. Have you done that? No? Yeah, okay. Now, what I want to show you it is easier for you to compare. What I'm showing on the screen are the estimate from ML, maximum likelihood. What you have just done is MLR. If you look at the chi-square, do you notice that the chi-squares, we have the same degrees of freedom, but the chi-square is a little bit different? If you look at your results, you will notice that there are two columns. The first column is based on maximum likelihood. The second column is based on MLR. The chi-squares are a little bit different. If we look at CFI, they should be a little bit different, but probably when I generate the data, I use normal distribution to generate, okay? So you will see two columns of CFI as well. There is, first column is based on maximum likelihood. The second column is based on MLR. On slide 107, okay, I will put it here. You will notice that there are three sets of CFI and TLI, three sets. First set on the left column, first column, it is by maximum likelihood. On the right-hand column, these are by MLR. But for MLR, there are also two sets. The first set is based on the equations based on M+. The second set, do you notice that it calls robust CFI, robust TLI? It is based on an equation developed by the author of Laverne. I don't use those. So I do not use those. Remember, use the first set in the second column when you report the CFI and TLI. Similarly, for RMSEA, you have the first column by maximum likelihood. The second column, these are by MLR. It is they are exactly the same simply because when I generate the data, it's normally distributed. So here you should look at this section of the RMSEA. Don't look at the robust RMSEA because it is based on an equation which is not very popular. And then we have the SRMR. Now, what I want to show you, the difference, now you see the difference of the fit indices. If you look at the estimates, you will notice that the estimates are exactly the same between the two methods. However, the standard errors are a little bit different. This is from the ML. What I'm showing on the screen are the estimates from maximum likelihood, but you have just done your estimates with MLR. So the standard errors are different. What that means is MLR and ML, maximum likelihood with robust standard errors, MLR, and maximum likelihood will give you the same estimates, but it will only adjust the standard errors. It will only adjust the standard errors. So MLR provide you with better standard errors because it doesn't assume it can handle some deviation from normality. Okay? I don't know where I should put. So we'll deal with MLR already. Any questions up to now? We ran a measurement model. So now you learned how to run a measurement model and you know how to run your estimates with MLR, maximum likelihood with robust standard errors, and also you know how to read the fit indices of MLR. If you don't have any question, I will move on to the major topic that I want to cover today is the criteria for measurement quality. If you read empirical studies in journal articles, you will notice that before the authors test the hypothesis, the first paragraph they will talk about is the descriptive statistics, table 1. And they will talk about the measurement quality of their scales. They will report the Comax alpha reliability, and sometimes they will demonstrate validity. But in marketing, we have a more stringent criteria. Marketing is doing much better than management in testing validity. So I borrowed from the concepts in marketing and write a paper. And I hope that people in management can also adopt the best practices for testing reliability, convergence, and discriminant validity. So we published this paper in 2024 in Asia Pacific Journal of Management. When we measure the quality of scales, there are two ways that we measure. One is about reliability. You should be very familiar with reliability already because all the scales that we report the Comax alpha. Comax alpha is a measure of reliability. If you miss this out, your paper will get rejected. Okay, reviewers will ask you for the reliability. For validity, interestingly, marketing people require all the studies to report validity, but management people, they don't report validity. There are different concepts of validity, including phase validity, criterion related validity, construct validity, and content validity. But in measurement scales, what we are concerned about is convergence validity and discriminant validity. These are the things that we can test with structural equations modeling. So what are the backgrounds? Okay, many constructs in our studies are latent constructs that cannot be directly observed, like attitudes, perceptions, behavior, intentions. Okay, we use established scales with multiple indicators to measure these constructs. Okay, we use 3 items or 4 items or 5 item scale. And yesterday I told you that you should not develop your own scale. what you should do is to use established scales. That means people have published the scales. Okay. Try to use the scales that are more popular, that has been used multiple times, because they are more reliable. Don't use a scale that has just been published last year and used once or twice. Okay, they may not be good scales. So we use established scale instead of creating your own scales, multiple indicators. Reliability, convergence, and discriminant validity should be reported for all latent constructs. Okay. These are the basic requirements that we should report before about the quality of your scales before we test your hypothesis. The problem in management is that researchers use different approaches and standards to test convergence validity and discriminant validity. Therefore, the studies are not comparable, the scale of the quality. If you use one method to test discriminant validity, and I use a different method to test discriminant validity, then we cannot compare the quality of our scales because we use different methods to test discriminant validity. The purpose of this paper is try to establish a best practice recommendations and ask people to use a standard procedure to test reliability, convergence, and discriminant validity. One more thing is most studies ignore the sampling errors. When we test our hypothesis, we divide our estimated parameters by the standard errors because we know that we are collecting samples. We talk about confidence intervals. These include all the sampling, these represent all the sampling errors. However, when people test their reliability, when people report, for example, complex alpha for their reliability, they never talk about sampling errors, as if the complex alpha of their sample is the same as the complex alpha in the population. So it is wrong. We should incorporate sampling errors when we test reliability, convergence, and discriminant validity. So definitions of convergence and discriminant validity in multi-trait, multi-method context is more than 60 years ago. First, who introduced convergence and discriminant validity is Campbell and Fish. They define convergence validity as if you use two different methods, very different methods to measure the same construct, then the results should be highly correlated because you are measuring the same construct. That is what they refer to as convergence validity. If you use different methods to measure the same construct, then the two measures should be highly correlated. For discriminant validity, is that if you use the same method to measure different constructs, the correlation should not be too high. This is what we call discriminant validity. Okay? The problem for Campbell and Fish, that is what we use MTMM, multi-trait, multi-method. That means multi-trait means that you have different construct. Multi-method means that you measure the same construct multiple times using different methods. The problem is, in all the empirical studies, it is so difficult to collect data. Collecting data using one method is so difficult already. How can we collect data using multiple methods, different methods? It is not possible in empirical studies. Therefore, Bergossi, a marketing people scholar, in 1981, he redefined convergence and discriminant validity in SEM. Convergent validity means that the measures of the same construct, here, the measures refers to the items or the indicators of the same construct should be highly correlated among themselves. That is how he defined convergent validity. So he treat each item as a different method in SEM. So the items should be highly intercorrelated. For discriminant validity, again, post-construct correlations should be at a lower level than the within construct correlations. So the correlation between two constructs should be lower than the correlations of the indicators for each construct. That is how he defined discriminant validity. Now, before the lunch break, I will quickly go over different methods for assessing reliability, convergence, and discriminant validity. First, reliability. How do we assess reliability? Typically, we use Compass alpha, and we want the Compass alpha to be greater than 0.7 or 0.8. Most of the studies will use 0.7 as the threshold. However, in the NOLI, in fact, the recommendation is 0.8. But nowadays, most people use 0.7, okay, because they don't want to throw away their data. So here, the reason why we need to have a minimum Compass alpha or reliability is that many years ago, 30 years ago, 40 years ago, how did people test before SEM? How did people test their hypothesis? They used t-test, ANOVA, and regression. T-test, ANOVA, and regression ignore the measurement errors as if you have no measurement errors. But then they also find that, so that's why they want to make sure that the measurement errors is not too big. That will affect the results. Therefore, they set a minimum of measurement error at Compass alpha equals to 0.7 or 0.8. Now, do you understand why we need 0.7 or 0.8? It is because when you test your hypothesis using t-test or correlation or ANOVA or regression, you assume that you have no measurement errors. But in fact, we have measurement errors. Therefore, you want to make sure that the measurement errors will not bias your results by too much. Therefore, you set a minimum of Compass alpha. The minimum should be 0.8. A lot of times people use 0.7. One problem for Compass alpha is that it assumes equal factor loadings across indicators. That means in SEM, it assumes all the factor loadings for the same factor to be equal. If you use submitted scale, you take the simple average score. Okay, so all the items are equally weighted. But in SEM, we estimate the factor loadings. It assumes that all the factor loadings are the same. If we look at our previous example, you can see that the factor loadings are not all the same. Example for MM, first factor, here, okay, we should look at the standardized all. For the second construct MS, the first item has factor loading of 0.922. The second item has 0.56 and the third item is 0.444. So they vary a lot. In this case, Compass alpha is not good. Compass alpha assumes that all these factor loadings are the same. And why Compass Alpha is so popular? Because a lot of people don't realize the problems of Compass Alpha. The assumption, there are two assumptions. One is multidimensionality, unidimensionality. The second is that the factor loadings are the same. A lot of people don't aware of the problems. Okay, so they use it. It is so easy to estimate because SPSS, all other softwares can give you this. It is widely accepted. The major issue is if you do not report Compass Alpha, the reviewers will ask you to report Compass Alpha. Will ask you for the Compass Alpha anyway. Okay? There's another measure of reliability. We call this construct reliability or composite reliability. It is based on SEM. Based on SEM, the lambda are the standardized factor loadings, completely standardized factor loadings. This is the equation how you calculate construct reliability. It doesn't assume tau equivalence as in Compass Alpha. That means it doesn't assume the factor loadings to be the same for all items. The criteria, this is the citation, okay? We use 0.7 as well, 0.7 or 0.8 for construct reliability. So now you have two measures of reliability, construct reliability and Compass Alpha. I think about all studies, almost all studies, I think about at least 80% of the studies report construct Compass Alpha. Over 80% of the studies report Compass Alpha. 20% reports only construct reliability. And about 50% of the studies report both Compass Alpha and construct reliability, which is actually unnecessary. Okay? I found that construct reliability and Compass Alpha are highly correlated. Now, which one should you report? It depends on how you test your hypothesis. If you test your hypothesis with a path analysis, that means you assume that your items do not have measurement errors, then you should use Compass Alpha. If you test your hypothesis with a full structural equations model with latent variables, then you should report the construct reliability. Okay, there are two ways. I will repeat it later on today. Now, do you understand the difference between Compass Alpha and construct reliability? Compass Alpha assumes the factor loadings to be the same across items. Construct reliability relaxes this assumption. Therefore, we have a different measure of reliability. Both use 0.7 or 0.8. Are you okay?
Yes.
Okay, because I'm going to talk about a more complicated model. A second order factor. By definition, second order factor is not unidimensional because second order factors are multidimensional. Second order factor are multidimensional. Here, engagement, it has 3 dimensions. Each dimension measured with 3 items. Compass Alpha has an assumption of unidimensionality. Do you know how Compass Alpha will calculate? How we calculate the Compass Alpha for engagement? It ignores the second order structure. It just assumes that engagement is measured by 9 items. So it totally ignores the second order structure. That is wrong. What that means is, if you read a journal article and they have a second order construct engagement, for example, and they report the Compass Alpha, then you can say that it is wrong. You should use a different measure of reliability, which I'm going to tell you what it is. Here, a second order factor, okay? The first equation is expressing the relationship between the dimension and the item. X, the observed variable, equals the factor loadings times the psi plus the error term. And then we have a second level, either the engagement is either. It also has the factor loading, we call this gamma. And we use this to predict as if these are indicators. We use this as observed variable, psi equals to gamma eta plus omega. These are the residuals. It is very similar to here. Okay? We have a latent variable and three observed variables, and we have factor loadings and the error terms. This is the first order structure. For the second order structure, you can see that it is more like we use these three as indicators. This is a latent variable, so the factor loadings, now we call this gamma. And we also have the residuals, omega. Can you see that? Okay, so we have this part and this part. Now, if we want to look at the effect from engagements to your item, does it look like an indirect effect to you? From engagement full rigor to X, or from engagements to dedication to X, or from engagements to absorption to X. Does it look like an indirect effect? So the relationship from engagement to X is simply the product term of gamma and lambda. Okay, so if we combine these two equations, we will get the third equation. From your second order factor, either we multiply the lambda and the gamma that represents the relationship of X. There are two error terms. The first error term is the eta here, the error term. And other error term is the omega times the lambda. No, it is very complicated, but if you treat it as an indirect effect, you can see that from engagement to the item, it is gamma times lambda. So the first term. And then there are two error terms. One error terms associated with the items. The other error terms associated with the dimensions. Second term are the error term associated with the dimensions. The last error term is the error term associated with the item. So how do we find the reliability for second order constructs? In fact, we divide our X, we partition our observed score X into three components. One is the component, the true relationship from engagement through your dimension to your item. And then the second term is the error term due to the dimension. And the third term is the error term due to the item. We can create an equation like this. We can decompose the variance of the observed score into three components. One is the true relationship from your second order factor to the indicator. You can see that we multiply all the lambdas and gammas. The second term is the sum of all the error terms due to the dimensions. The last is the sum of all the error terms due to the indicators. Just like here, we have the relationship from the second order factor to the item. We have the error terms due to the dimension, and then we have the error term due to the items. So we decompose this into three components. Based on the classical test theory, reliability is 1 minus the variance of the error term divided by variance of the observed score. Therefore, McDonald defines two reliability measures. Let me talk about the omega hierarchical first. Omega H. Omega H is the variance of the true score. Okay, we have the variance of the observed score. We partition it into three parts. The variance of the true score plus the variance of the error due to the dimensions plus the variance of the error due to the items. So omega H is the variance of the true score divided by the variance of the observed score. It is the definition of reliability with omega H. It is more appropriate reliability measure for the second order factor because it is the variance of the true score divided by the variance of the observed score. It is the definition of reliability in classical test theory. However, some people also introduce another reliability called omega total. So omega total is to combine the variance due to the true score and the error variance of the dimension divided by the variance of the observed score. So here, basically, what that means is we only parcel out the variance of the item score. Omega total is a measure of the reliability of the dimensions only. It is not the reliability of the second order factor. The reliability of the second order factor is omega H. Omega total is the reliability of the first order factors or what we call the dimensions. Some scholars suggested that we should use omega total. The only reason is because you add another square term here, omega total is usually higher. The reliability looks better than omega hierarchical. But omega total has in fact ignored the fact that the engagement cannot explain all the variance of your dimension because it has ignored the residual variance of your dimensions. So let me summarize. For reliability, we first use convex alpha. But then we know the problem of convex alpha. The problem of convex alpha is that we assume the factor loadings are the same. Therefore, we use construct reliability, which is based on this equation on slide 122. The lambda, we allow them to be different across items. For second order factor, we should use omega H. That represents the reliability of the second order factor. That represents the variance of your true score of the second order factor divided by the variance of the observed score. If you use omega total, you are talking about the reliability of the dimensions. You're not talking about the reliability of the second order factor. Do you want a lunch break now? Or you want me to continue?
Lunch break.
I'll give you a lunch break now. I think you need time to. I think you may need time to digest about the reliability. Okay, let's take a lunch break and let's come back at 1. Okay,
Thank you, Gordon.
good. Okay, I'll see you in an hour.